Okay, time for another AP Chem video. This one is going to be on topic 1.4, which is the composition of mixtures. And I'm going to kind of do this one off the top of my head instead of my normal video that I've been doing for the last few ones. So with the composition of mixtures, what we're talking about there is really an add-on to this idea of empirical formula. And often you see 1.3 and 1.4 discussed together. Usually you're going to see this asked on the AP exam in the form of a lab question, and the lab that we would do on this is called gravimetric analysis. And the idea behind gravimetric analysis is really that you get mass data, and then you use that data to determine the formula of a compound, or in the case of topic 1.4, a mixture. So what could this look like? So often what we do is with the mixture, we often dehydrate it. So we'll take something that's called a hydrate, and a hydrate is usually an ionic compound that's got some water that just kind of naturally associates with it. Now, those waters are predictable in the number of waters that will surround each formula unit of an ionic compound there. And so you can determine what the formula of that hydrate is. So really common one that we use is copper sulfate or copper chloride. And you can have CuCl2, and then you see a dot in the middle, 2H2O, okay? And so then that's two waters that are surrounding each unit of copper 2 chloride there. So we can do the lab. Now, what we often see with this is that you remove the water in some way. So often you heat it either in an oven or over a Bunsen burner, and then you measure the mass. And so you would put your hydrated sample in some kind of vessel, often a crucible, okay, or an evaporating dish, and you would get the mass of that before. Then you would heat it for a period of time, usually 5 to 10 minutes, and then you get the mass again. And then you'd heat it again, and you get the mass again, and you heat it again, and get the mass again. And you stop heating it when the mass stops changing. And that's important because that's where a source of error can be. If you do not heat it enough times, you might not remove all of the water. And if you don't remove all of the water, then your data will be thrown off, because what you will assume is all copper chloride in this case, or copper sulfate, or whatever it is that you're examining, is actually got a little bit of impurity in it in the form of water. And so then that would skew your data. It would make your mass of your copper compound too high and the mass of your water too low. Now, in terms of calculations, you do this exactly as you would do an empirical formula. You take your mass data and you convert it to moles, and then you do a ratio, okay? And so you can actually find the number of waters of hydration, again in this example, by dividing your moles of water by your moles of your, again in this example, copper compound, right? And so that's the way that you would do this, and this is why we call it a mixture, because you have this water that's in there. Now, it's not the only way to do it, right? So you could also examine the composition of an alloy in a way like this, or we've also seen it done in like a tablet. So the tablet's got some kind of filler and then something else in it, or you can do some kind of selective precipitation where you might have a mixture of two compounds, and then you add something in and you precipitate one of them, and then you can figure out what the makeup is of that mixture. So in that case, you would be doing more of a percent composition calculation, and with that, all you need to remember is that a percentage is a part over a whole. So if you have a tablet and you're trying to figure out what percent of the tablet is this target whatever substance, compound, whatever it might be, element that they're looking for, you can figure out, you can go to moles, right? And then usually for percent composition, we would do that in some kind of mass way. So that's the main thing with 1.4. Now, a lot of times we see this asked with data tables, and then they like to ask about sources of error. And what you need to remember with that is you need to think about where the error is, how it's impacting your data, and how it's going to impact your calculations. So normally what we see is we see some kind of contaminant that's going to drive the mass of the target ion up, and the other component, often water, down. Or we see some kind of incomplete reaction or something like that where you don't collect all of the target ion, or maybe you lose some of it because it washes through the filter or something like that. So a little bit different video, but this one is kind of got the same math as what we talked about in 1.3, but with a little bit of a different situation. So I thought I'd just come on here and give you some things to think about.